All right, so today on my amazing desk full of cords, I will be talking about this custom Proto head tube that I built for this deck. So this obviously is just the deck that Proto sells, but then this is the custom neck for it that I designed. Of course, one of the inspirations for this head tube was Proto decks and how instead of using a welded system, they have these little grooves on the side that slide into the deck, which keep it secure while you ride. Beyond that, I was inspired by the original Tilt Theory deck design, which has a good strength to weight ratio, which is achieved by using the widest tubes possible. So as you can see here, rather than this head tube tapering inwards the way that a lot of head tubes do, it just has a flat side and it's as wide as possible, which means that it can be thinner without being super weak, as opposed to a skinnier tube, which would have to have thicker walls in order to maintain the same strength. I was also inspired by drone decks for their lattice that saves weight on top of the deck, so I wanted to implement something like that in my design. I was inspired by NVAOS V6 decks, which have these two vertical walls in the head tube, as opposed to having a strong top and bottom, or in this case, any top and bottom. I was inspired by just ethic decks in general because they all look very, very good while also prioritizing weight reduction, especially the Pandemonium decks. And then finally, though I did not do anything to visually represent native decks, I really like the small blunt space they have, so I implemented that into my design as well. As is labeled on my original prototype here, the head tube angle is 83.25 degrees. The reason for this is that my favorite head tube angles to ride are 83.5 and 83. Because of the weldless system, there's a teeny tiny bit of wiggle room, so maybe this will lean slightly back or slightly forward, even if by only a really small amount. Either way, by having it between those two head tube angles that I like, if it leans the tiniest amount forward or the tiniest amount back, it'll still fall within a range of head tube angles that I feel good riding with. A small detail which I'm glad I included is my Taro brand leaf bowl logo. Of course, I don't have an actual scooter brand, but I think it's cool to have my little signature on the parts that I make. Bigger picture, this was SLM printed out of titanium. The reason that I did that is because SLM printing sometimes makes weird grain structures or has other issues, meaning that if I have something that's SLM printed out of aluminum, for example, and then CNC machined out of aluminum, the CNC machined one will be stronger. So as a consequence of SLM printed parts being weaker than their otherwise manufactured counterparts, I wanted to use a stronger material than head tubes are usually made of in order to compensate for this problem. On the newer Proto head tubes, these holes will have threads inside of them such that when you put your hardware through here, they can screw directly into the head tube. I decided to utilize the old TDI pin design, meaning that I do not have to have threads inside of my head tube. The reason that I chose to do this was because initially I was doing research on how to 3D print threads, but due to rough surfaces produced by 3D printing metal and the potential difficulty of cleaning up imperfections on small internal threads, I opted for a threadless design. As a side note, it's of course possible to just have holes machined like this and then in post-processing have threads added, but it's already expensive enough to prototype as it is, so I wanted to keep costs down, especially because putting threads into titanium is more difficult than it is to do so with softer metals. For the top and bottom of the down tube, I inserted very large cutouts here in order to reduce weight, and these were, as mentioned earlier, largely inspired by NVAOS V6 decks. For the sides of the down tube, I was unsure of how to reduce weight without losing too much strength, and upon researching patterns often used in engineering, I settled on a basic isogrid or isogrid-esque pattern. These aren't true hexagons, they're a little bit oblong, but it's essentially an isogrid. I also sunk the walls in slightly where I have this pattern, just to reduce weight a little bit more, even where these metal walls still do exist. On the bottom of the neck, I have the smallest reasonable amount of metal possible. Of course, I have this bolted in so you can't see it super well, but here's what it looks like from the top down. And then I have the STL file loaded up here, and as you can see, I've reduced a lot of weight by removing metal where it is not needed. Some other small details, which may be hard to see on camera, is that I have chamfers on the headset cups, so it's easier to put the headset bearings in. And then I also have very small chamfers on the corners of the down tube, just so that they're not as sharp when you're touching them. When I was making this, I noticed that it was hard to find resources online regarding the specifications of headset bearing cups for scooter decks. So upon talking to people and doing my own measurements, it turns out that if you want your bearings to sit flush, which you will want for the bottom of the deck, but you might not want for the top, if you want them to sit flush, this vertical wall, ignoring this chamfer, should be 5 millimeters high. And then of course, this angle downward is to fit the 45-degree angle of the bearing. So in a drawing form, it's something like this, where this right here, this little blue line, would be a cross section starting at the right side of this head tube. So there would be at the top right here, the teeny tiny chamfer. So from that point there to down there, which would basically be from this top edge to right there, that is 5 millimeters. And then the chamfer is 0.5 millimeters, so that's the vertical distance from those 2 points. And then that angle there between those dotted green lines would be 45 degrees, as is the case with down there where the bearing would sit. Throughout my design, I also made sure to include fillets in order to increase the strength of my product and to decrease the likelihood of cracks forming. Based upon the engineering research that I found, it seemed that there were diminishing returns when using fillets with a radius any larger than 0.6 times the wall thickness. So that's how I decided upon the size of the fillets throughout my part. As you can see, I also have them here. I have them, you can't really see in this angle, but I have them on the sides of this head tube. I also have some outside on the top and on the bottom. I will say that if I were to do this again, I would make all of my fillets much larger, not necessarily just for strength reasons when resisting a single impact, but for longevity as well, because the sharper that a corner is, so a good example is right here as well, the sharper that a corner is, the more likely that a crack is to form there. So if I was to make a head tube from scratch again, I would have the whole thing be way, way smoother and more organic looking than this one. 3D printing gives you more design freedom than CNC. What this means is that not only was I able to use the tilt-inspired idea of having a large head tube, I was also able to, where usually this wall here would just come straight down, I was able to thin it out so that it is thin here, it's thick here, and then for as much distance as possible, it's thin. That way, a lot less weight and a lot less material is needed in order to support the design. Of course, a more obvious way I reduced weight is by just having big old holes slammed through the front and the back of the head tube. A common height for scooter head tubes is 110 millimeters. Mine is close to that, but I made it slightly shorter just so that any SCS forks used with this head tube would have slightly more clearance and slightly more clamping room. When I was designing this, I didn't know if my dimensions would be perfect. As a consequence, I made the down tube slightly skinnier than the slot of the deck it would need to slide into, such that if sanding or post-processing was needed to ensure proper fitment, I wouldn't be sacrificing the integrity of the down tube by removing material from it, but rather, if I had to do any sanding to make this fit perfectly, I could just remove these little pieces here, sand them down a little bit, and it wouldn't sacrifice any structural integrity, but would allow the head tube to fit into the deck nicely. Fortunately, no sanding was needed, so perhaps in the future I can just make the whole head tube one width. Ignoring all of the weight reductions I did in the final product compared to my prototype, the only geometric differences are that Right here on the bottom of the head tube, I've extended it a little bit in the final design so that my fork sits lower to the ground so that the wheelbase is more even. And then these holes were also a little bit in the wrong spot on the original design, so I've adjusted them such that the little plate right here sits exactly flush with the front of the deck when the hardware is screwed into the holes, which was not the case in the original design, in which this part stuck out slightly and did not look as good. For anyone looking to do something similar, I had this prototype made out of FDM plastic via JLC 3DP, and then I had this made using Craft Cloud's website, which I then used to select the vendor Shenzhen 3D Innovate, and I think both of these turned out very well. The reason I used a different vendor for this one is because I wanted more competitive pricing. For cost reasons, I did not have this part heat treated in any way, but if I chose to do so, I would have it vacuum annealed at 750 degrees Celsius for 2 hours, and then furnace cooled under protection of vacuum and or argon. I won't bother reading all this stuff, but if you're interested in looking at the sources I used to determine why I would heat treat it this way, feel free to do so. In the last clip, I said that this wasn't heat treated in any way. So that's not completely true. I just contacted Craft Cloud and they said that Shenzhen 3D Innovate did perform stress relief treatment to prevent deformation, which does benefit the lifespan of the part. That said, I still do think it would benefit from another form of heat treatment, such as the annealing that I mentioned, because that way the material could stretch a little bit more before finally reaching its breaking point. This design does not have any top or bottom walls, but if I was to design a head tube in the future that did have those, I would make sure to have them have either a concave or convex design, such as with the native format deck that I'm showing right now, because that would be a bit more aesthetic than just having it straight, and it would also increase the strength by making it hard to bend in this direction. Finally, I'll end with a note about designing in general and then designing for the 3D printing process. So for general designing, if I was to make a head tube in the future, I would have it so that the width of the down tube comes up and then matches up perfectly with the width of the head tube. I think that would make designing a lot simpler and I think that would look a lot better. Likely, if I did that, I would find some way to basically rid all this material right here, such that the only material that existed would be on this outer edge out here. I don't quite know how I would do that because then these bearings up top would just slide right out, but I would figure out a way to make something like that work. For the 3D printing specific advice, as you can see, I have a little line right there that is a consequence of how thin this wall becomes. So instead of having it be super thin because there's an angle right here, I should have just shot a hole straight through it as opposed to at an upward angle through it. And as you can see, this caused a little bit of printing errors. So right here where this line is, it also exists throughout the entire print. You can't see it as well, but it's on this side too. There are a couple other areas of this head tube where that also happens, but the lesson I learned is to try to have no thin walls in the printing process, otherwise it will cause some anomalies such as those I just showed you. The purpose of this project was to better teach myself how to use 3D design software, in this case SketchUp, and in that manner I think I was quite successful as I became much more efficient at using that software. There's of course a lot that has to be improved about this design, but for my first attempt at making a scooter head tube, I am very happy with how it turned out. I will now end by putting a couple pictures of it on the screen, and overall this project in my mind was quite a success.